Hello, today we're going to talk about electromagnetic waves, light, and how electromagnetic waves interact with different materials. So electromagnetic waves are light waves. Sometimes electromagnetic spectrum, which would be all the different types of light. Sometimes it is called electromagnetic radiation. Don't get confused with that, because electromagnetic radiation would be like if you put your you put your hands near a heater and you would feel that heat. Okay, that heat would be radiating towards you, right? It's traveling towards you. Not the same as radiation as in a radioactive material. So don't let that confuse you when you hear that in the future. So light is an electromagnetic wave. Electromagnetic waves are waves created by vibrating electric charges. Okay, we're going to break that down to even simpler terms in a moment. Electromagnetic waves can travel through matter, empty space, and they can have lots of different frequencies and wavelengths. So light waves, which were discussed earlier, are not mechanical waves. Remember, mechanical waves can only travel through something. Sound can only travel through a medium. Light waves, they don't need that. They can travel through the vacuum of space. On the right in this image, you can see the many different wavelengths. As you go up, they get larger. As you go down, they get smaller in the wavelengths. So radio waves have a very long wavelength. They can go a kilometer. Right? The wavelength can be taller than a building. And when you look at the frequency, as you go down, there's a much higher frequency. Remember, that's how many times the wave goes back and forth, how many times the wave passes a certain point each second. So you get higher energy as you go down, lower energy as you go up. And if you look at the picture, you can kind of think about it. Radio waves are going through our body right now. You may not be listening to the FM radio right now, but radio waves are traveling through our air. It's not really affecting us. As you go down, something that we're very familiar with, ultraviolet rays, UV rays, or X-rays, those are high energy, and those do affect you. UV rays gives you a sunburn. X-rays, if you have too much exposure to them, can give you cancer. So something to think about, and we'll discuss that later. So electric vibration to magnetic vibration. So we have this electric charge that's vibrating, and this electric field has a magnetic field surrounding it. Okay, so as the electric charge vibrates, the direction of the magnetic field changes directions. Okay, so it's got that wave-like property. The changing electric field creates a changing magnetic field. The changed magnetic field then changes the electric field. So we have seen how electricity is associated with magnetism. And we see here we have this electricity magnetism relationship. So the electric magnetic field vibrate at right angles to each other. So this is useful in engineering and planning and designing. In the image to the right, you can see the electric field is going up and down. That would be the blue. And the magnetic field would be going side to side. And the direction of this electromagnetic vibration would be going up and to the right. So the thing you need to know is electromagnetic fields have an electro and magnetic component. So electromagnetic waves, they move, they hit objects, and they can exert forces on the particles or materials. For example, the one that I have here, light from the sun transfers the electromagnetic wave energy to your skin to create warmth. Okay. If you don't want that energy in a hot summer day, you go to the shade. So what happens is electromagnetic waves from the sun, they hit your skin, and there's electrons in your skin, and those electrons gain energy, and eventually you feel that as warmth. This is a similar way that you go up to a fire, all of the infrared radiation from the fire, you could feel that as heat if you're sitting around roasting marshmallows. So I have assigned an Ed puzzle to Professor Dave, and he will discuss the wave-particle duality of light. And as you get very, very small, the things that we have learned in physics, they are not the prevailing way that the universe works. So large objects, for all the things that we've discussed with gravity, with inertia and momentum, with velocity, and everything that we've talked about, and we were able to quantize, which we were able to calculate and put a number to determine how much energy is in things. Well, as you get smaller, things don't behave naturally. Things seem supernatural, and they call it the quantum world. Light is the same way. Light behaves like a particle, like it's a material, and it behaves like a wave, like it's a vibration in motion. And the reason why light can behave like a particle is because it has photons. Photons are the particle of light. So photons are tiny, they're massless, and they carry energy. So currently, with our current technology, we have determined that photons are particles, they are materials, but they don't have mass. I don't understand that, right? But as we get down to the quantum level, things don't behave like you think they should behave. And so the energy of a photon is completely dependent on the frequency of the wave. And the properties of light, they're dependent on the amplitude of wave. So there's two different things. There's the frequency of the wave, and that'll tell you how much energy a photon has. And then there's the amplitude of the wave, and that'd be kind of like the brightness. Okay, so for example, light, that not all light is useful to plants. Plants need a certain color of light to help them produce energy. So for example, green light will not help plants grow. All right, that's a pretty interesting thing. Even if you had a really, really, really bright green light, it won't help the plants grow, okay? So it has to be the proper frequency. As you change the frequency, you could get the different color. So even if you increase the brightness, the amplitude of the light, it wouldn't change. So those are two different properties to think about. Amplitude would be kind of the brightness, and the frequency, you could think of it as the color, but as you get outside the visible spectrum, it'd be everything from changing the frequency, you're getting everything from radio waves to microwaves to gamma waves. All right, so just an image right here. So at the top, you have a high frequency, high energy wave, and then at the bottom, it's low frequency, low energy. So think about you had a rope. If you're moving the rope up and down to try to get waves, would it require more energy to get at the bottom? You see two waves, and at the top you have many waves. Which one is going to require more energy for you to do? 2 waves per second or let's just say that's, I didn't count it, let's say it's 10 waves per second. Which one's going to require more energy? They're both the same height. Which one require more energy? Well, of course, the high frequency, high energy one of 10 waves per second would create more energy. It's a good thing to think about. Whenever I'm thinking about which one is high energy, I think about actually shaking the rope myself. This is an image of the entire electromagnetic spectrum, and you can see that all the way to the left you have very high frequency, all the way to the right you have low frequency. And you also can see to the right you have a very large wavelength, and to the left you get a very small wavelength. Radio waves, they say it's 10 to the 3 meters. So tall as a building. Infrared waves, the tip of a needle. Okay. Visible light is about, it says 0.5 to times 10 to the negative 6, so 0.000005 meters, pretty small. And that's the limit of being able to see things with a microscope, is through the visible light. So as you get to molecules, which is 10 to the negative 8, you can't see molecules with a microscope. There are other tools we use, but you can't see molecules with a microscope because the visible light is so long, or excuse me, the wavelength is so long that it just skips right over it and you can't see it. And that's why you can't use a microscope to see atoms. You have to use something smaller, different kinds of light. All right, we're not doing the warm-ups. There's going to be another Professor Dave that I'm going to have you watch on Edmodo. We're not going to watch it here, but I'm going to assign it, or not Edmodo, I apologize, to Edpuzzle. I'm going to assign that, and so be looking for that. So the double slit experiment. So this is really cool. So in the image below, you can see that they're using electrons. It works with light. If you had a laser pointer, this would work. So if you had a piece of paper, and you had two rectangular holes really close together, all right, because laser pointer has a very small beam. You put those really close together and you shine light to it. Well, you would expect to see two holes come out on the other side of the wall. That's not what happens. You see many holes. And so the double slit experiment was an experiment to determine the properties of light. So in this example, it works with electrons, and you've seen that on the Professor Dave if you're watching this afterwards. If you shoot a beam of electrons at the two tiny slits, what you're going to see is the electrons behave just like light, and it diffracts just like waves. We talked about diffraction last week. And the particles will show interfering patterns. And so remember how you can have constructive and destructive interference? That's what you're going to see on the screen. So where you see the light for the electrons here, that would be the constructive interference. The blank spots, that would be the destructive interference, where it's canceled itself out. So like we said, the electromagnetic spectrum, the waves can have a wide variety of frequencies. That's what gives us different kinds of light. So we believe that we know the entire range of the electromagnetic spectrum, and we call that, that would be all the frequencies. And again, just to reiterate, electromagnetic waves are sometimes called electromagnetic radiation. The EM, talking about electromagnetic radiation, is radiant light, not to be confused with radioactivity. Those are two different things. Different frequencies of light interact with matter differently, and that is super important because that's how we can utilize these things and develop awesome things like solar panels. We've seen that slide before, so I'm going to continue on. So radio waves. Now, radio waves are cool. Next week, I'm going to show you how radio waves are used to transmit information, because that's where the power and the engineering and how you can make this cool. So radio waves are frequencies from 3 kilohertz to 300 gigahertz. That's a broad range, okay? You can't see them, you can't hear them, you have to use a mechanical device called a radio to hear it. Most commonly, radio waves use AM and FM radio, or AM and FM radios. You convert it into music using speakers, and we talked about how a speaker works. And next week we're going to talk about how they modulate that and what that means. So don't get confused. Radio waves are not sound waves. Radio waves are going through your house right now. You don't hear them. You need a machine to do it, called a radio. Okay, then there's microwaves. Microwaves are a part of radio waves. It's like a smaller portion, like if you zoomed in on radio waves, microwaves be part of it. So this is the range, 300 megahertz to 300,000 megahertz. So microwaves are a specific part of the radio waves, like I said. It's useful for satellites, cell phones. So you can see that cell phones use 700 megahertz to 2,300 megahertz. Microwave microwave ovens, they cook food at 2450 megahertz. So depending on where you live in the world, they use a different megahertz, a different piece of the spectrum to determine if they're going to use for what they're going to use for their cell phones. Obviously, you don't want to be at the 2450 range or you'll cook your brain. Radio waves got a lot of applications. So in the top right, you have a satellite image, and this radar that you see is what helps us predict the weather. And you can see right here, as I circled the mouse around Charleston, you can see how it looks like there's little blank spots. Well, that's because literally there's a radar going around in circles detecting it. That's also how we detect airplanes in the air. So they shoot out radio waves and they find the position and movement of objects. They can be very precise all the way up to tracking birds in the air. Now, magnetic resonance imaging, that's what you see down below. It's a medical technique that detects radio waves that have interacted with the hydrogen atoms of your body. And they do that when they've placed you under a strong magnetic field. And so as they go through this process, they can create a three-dimensional image of all your body's tissues and structures. Very useful. It saved my life before. When I had showed up in the emergency room, they found out something wrong, and they had to take care of me. So basically, they put you under a strong magnet, and it lines up all your atoms in a certain direction, and then they bounce radio waves at you, and it causes your hydrogen atoms to tip in a direction, and we can detect that, and then it lines right back up to the magnetic field. So as we're tapping it with the radio waves and it comes back, we can measure those waves and transform them to an image. A lot of mathematical processes involved, but really neat stuff. Infrared waves, okay, the heat waves. So at the top, infrared waves, that's what your remote control to your television uses. Interacts with the skin to create thermal energy as you feel warmth. Night vision cameras, they use an infrared light to illuminate areas to the camera, but you can't see it with the naked eye. So the middle image, you can see at the top, you see a security camera with light. At the bottom, it's a dark room, but they're using an infrared light to illuminate the area. So it's really interesting that the entire electromagnetic spectrum can be used to light up areas. We just can't detect it with our eyes, but we can detect it with other things. There's been some technology that uses light from your Wi-Fi routers to map out everything that's in someone's house, right? So the walls aren't really protecting you. You can map out what's inside people's homes by their Wi-Fi router. All right, that's pretty interesting, scary stuff. Thermal imaging at the bottom. detects infrared radiation waves, and you can see the difference in temperature. So really useful stuff. Visible light, that's the stuff we can see with our eyeballs. All right, it's very small part, red, orange, yellow, green, blue, indigo, violet. I've read some studies where they say women have just a little bit better at seeing the edges of colors than men can. So, guys, when the ladies tell you, hey, that doesn't match, listen. Ultraviolet waves, all right, they're high energy waves. They can cause damage to the skin, they cause cancer, they can cause DNA damage. You got two types of UV rays. You got UVA, UVB. You do need some ultraviolet radiation to help you synthesize vitamin D in the body. Too much is going to cause sunburn, wrinkles, skin cancer, freckles, moles, all that stuff. So you can see in the image of this lady, look, she has very nice skin. You can see on the left, but if you look at it with UV ray filter, you can see how much damage has been caused to her skin by being outside in the sun. So wear your sunblock. Even if you have dark skin, you still need to wear sunblock, okay? You are just as likely to have skin damage and risk for cancer if you have dark skin, all right? So that's a common misconception. Wear your sunblock. Other uses for ultraviolet light, well, they cause DNA damage. Well, we can use that to our advantage because it can destroy pathogens, it can destroy viruses, so it's used to clean medical equipment, and it's also used to purify water. You can get rid of the pathogens in the water because it'll kill anything that's living, and it will denature the proteins of viruses. So UV light right now is used to help destroy coronavirus on medical equipment. They can also cause fluorescent materials to glow as visible light, and you can see this in this really neat picture. There is a lady wearing makeup with fluorescent makeup, and they have a black light, which is primarily ultraviolet light. You can see a little bit of the violet spectrum, but bleeds over to UV rays, and it causes things to glow. And you can see that down below. X-rays and gamma rays. All right, we're getting to some nasty stuff. So the wavelengths from 10 billionths to 10 trillionths of a meter. That's pretty small, guys. Most of us have had X-rays before. They use it for medical tests. They screen baggage in the airports. Gamma rays are the shortest wavelengths and the highest energy wave. This stuff is some nasty stuff. Both of them can kill living tissue and biological molecules, and so whenever you get radiation treatment, it's either going to be X-rays, and more than likely it's going to be gamma rays, and they're going to use that to kill cancer and tumors and diseased tissue. All right, guys, so that's it for this lecture. I hope everybody is well. Don't forget to do your ed puzzles. We have 2 weeks remaining, and there is going to be a final project posted. So let's get the work done. We're almost at the end of the race, so it's time to sprint. 2 more weeks. You got this, guys. Be well.